Now we'd like to look at using capacitors as circuit elements. To use capacitors as circuit elements, we'll need a symbol to put in our circuit to represent the capacitors. So the first thing we need is to figure out an appropriate symbol. The common symbol for a capacitor is simply two parallel lines that represent the parallel plates of the capacitor itself. The capacitor is also used with the passive sign convention, which means that if we have a current flowing into the capacitor in this direction, then the voltage is taken as positive in this orientation. In some applications, the polarity of the capacitor or its orientation with respect to the circuit nodes is important. For these cases, a polarized capacitor symbol is used instead. In this symbol, the curved plate represents the lower potential or the bottom plate of the capacitor. To use the capacitor in a circuit, we'll need a relationship that relates the current through the capacitor to the voltage across it. This is commonly referred to as the capacitor's IV relationship. We know that charge on a capacitor as a function of time is equal to the capacitance times the voltage as a function of time, but we're interested in a relationship between the capacitor's voltage and the current through the capacitor. Fortunately, we can recall that the current as a function of time is simply given by the time derivative of the charge. We can substitute in for the derivative of the charge with respect to time with the derivative of the voltage with respect to time, because we know that the capacitance is a constant. Consequently, we can write that the current through a capacitor as a function of time is going to be given by C times the derivative of the voltage across the capacitor with respect to time. And this relationship describes how capacitors' voltage and currents are related. Looking at this equation, we can observe two facts. The first one we note is that if the voltage is constant, its derivative will be zero. With a zero derivative, that means that the current through the capacitor will also be zero. Consequently, a capacitor with a constant or DC voltage across it has no current through it, and it appears like an open circuit. An open circuit implies that the current through the capacitor will be zero. The second interesting point to note is that if the voltage was to change instantaneously, the derivative would be infinite, and an infinite derivative implies that the current must also be infinite. If we have an infinite current and a finite voltage, then the power will be infinite. And we know that from a practical perspective, we can't have infinite power. Consequently, we can't have infinite current, and therefore this implies that the voltage across a capacitor cannot change instantaneously. We will use these two observations when we start to analyze circuits in our later discussions. While the relationship we've just found for the capacitor's voltage and current is useful, we have to know the capacitor voltage to find the current. Sometimes we know the capacitor current and wish to find the voltage. So what we'd like to do now is to determine how to find the capacitor's voltage if we know the current. The obvious thing to do would be to integrate both sides of the equation that we have up above. An alternate approach is to go back to the basics and recall that the charge as a function of time is equal to the capacitance times the voltage as a function of time, which we can always rewrite and say that the voltage across the capacitor as a function of time will be equal to 1 over C times the charge as a function of time. And recall that charge as a function of time is the integral of the current from minus infinity to the desired time. We can re-express that as an integral from some starting point, t0, to the desired time of the current plus the initial charge on the capacitor. We can make this substitution into the equation for the capacitor voltage. To find the capacitor voltage as a function of time is going to be given by 1 over C times the integral of the capacitor current over time plus the initial charge on the capacitor divided by the capacitance. If we recognize this last term here as simply the capacitor voltage at our initial time, we can rewrite the voltage across the capacitor as a function of time in the following form. We'll have 1 over C times the integral from our start time t0 to the desired time of the current through the capacitor plus the initial charge or voltage on the capacitor at the start of the integration interval. In many cases, we'll find that the initial charge on the capacitor is 0 or the initial voltage is 0, and the equation is simply the integral of the current from the start of the time of interest to the time that we want to know the voltage. We'll turn now to a quick example to see how to use these equations.